This video will be an introduction to work and energy and impulse and momentum. At this point in the semester, we should have three equations well understood. A is defined as dv dt. V is defined as ds dt. And if we combine those two, we know that A ds equals V dv. So we have two different definitions of acceleration from those. We have this one, and then we can rewrite this bottom one as A equals V dv over ds. And so many problems can be solved, if not all problems. F equals ma. And the first few examples, it'll only be a little bit easier using work and energy or impulse and momentum. But in reality, especially your future courses after dynamics, you're going to be using variations of the work and energy equations and variations of the impulse and momentum equations to solve more complicated systems, where you look at flow, whether it's burning gases out of a rocket or sewage going down a pipe, to get graphic with you, as a system of particles moving. And you're not going to really care too much about the acceleration. You're going to be more interested in the velocity or the location of it, the position. Sometimes you want to know how long it takes. But the actual acceleration, you're not going to be that interested in. So F equals ma has its place. I'm going to do a couple more videos where we use F equals ma, and then we do impulse and momentum and work and energy instead. We'll see that those simple videos, it's just a little bit easier, work and energy, impulse and momentum. But again, as the problems become more complicated and the parameters are more complex, work and energy and impulse and momentum are going to greatly simplify the solution. So with F equals ma, we can substitute those in. We have m dv dt, and we have m v dv over ds, v dv over ds. Just substituting them in, our two equations for acceleration. This here is our impulse and momentum, and this here is the basis for our work and energy equations. And most textbooks used to do work and energy first. The textbook we're using this semester has both of them in the same chapter, but it does work and energy and then impulse and momentum. I would say more than half of the textbooks usually have a work and energy chapter and then an impulse and momentum chapter, because it's so important. But so let's do the work and energy. I'm going to get rid of the denominator. And so I have mv dv over ds. I'll bring the ds over to the other side. So work and energy. I'll have f ds. And what I have left is mv dv. And if I integrate both sides, I don't know if I need to write it again, but I'll integrate both sides. And that's from S1 to S2. And I'll integrate both sides here, and that's dv, so it's from v1 to v2. The left-hand side of that equation is our work, that's a definition of work. Sometimes we use the letter U to represent it. The right-hand side is our kinetic energy. And so when I integrate that, I don't really want to integrate this now. If the force is constant, then you could integrate that and just, and S1 is equal to 0. You could integrate that just as F times S if the force is constant and S1 is equal to 0, or it's F times delta S if S1 is not equal to 0, so it would be delta S would be S2 minus S1. But I like to leave it in that form until I'm ready to apply it to a problem. So I'm just going to integrate the right-hand side. You could take the mass out because the mass isn't changing, but realize, back to the burning gases, mass does change sometimes, so mass doesn't always come out. But for everything in dynamics, everything in our course, it'll come out as a constant, and go V, V1, V2, and if we integrate that, we get M V squared over 2, and that's from V1 to V2, or written out, it's M V2 squared over 2 minus M V1 squared over 2. And the traditional, the way to remember it, or the traditional way this is written, is we take this and we move it to the other side of the equation. So we have the initial kinetic energy plus the work added. And I'll often skip the S1, S2, just kind of introducing it right now, is FDS is equal to the final kinetic energy. And so that's work and energy. When do we want to use work and energy? When the position, S, now maybe that's some distance D, maybe that's some location X or Y or Z, maybe that's some radial position R, but any of those. When the position is given or asked for and other parameters are there, but not time, right? When it's not a time problem. If the problem is asking you how long does it take for such and such to happen, you're probably not going to use work and energy. Right? But if it's asking about the velocities or the distance, we're probably going to want to use this equation to work and energy. The impulse and momentum is very similar. It's a little bit more straightforward. dt is in the denominator, so I'm going to bring that over to the other side, and I'm going to have f dt equals mdv. I'm going to do the same thing. I'm going to integrate both sides. I'm going to go from V1 to V2 and T1 to T2. And that left-hand component, again, this is the work. And this left-hand component is the impulse. Double ready. That's the impulse. Again, the mass could come out, or we can just integrate. We'll have the integral T1, T2, f dt is equal to mv, evaluated from V1 to V2, or mv2 minus mv1. And this is the momentum. My apologies, I have to move the page. I'm sure you can catch up. Integral of FDT is equal to the integral of MdV. Leaving that impulse in that form, integral of FDT, and then integrating the other side from V1 to V2 gives us MV2 minus MV1. And we call this momentum. This term is momentum at time 2. This is the momentum at time 1. And more specifically, later on, we're going to have to differentiate between linear momentum and angular or circular momentum. But right now, we just call it momentum, and that is linear momentum. And I want to do the same thing we did above. I want to take the initial momentum over to the other side and add to it the impulse, T1, T2, and that is equal to, add the impulse, and that is equal to the final linear momentum. Once again, if you have a question that's asking you about time and associated velocities, or a force that produces certain velocities, this is the equation you want to use. You're not going to use this equation if it's asking you what's the position of a particle at some future time. So, working energy, impulse, and momentum. The next part is if no external work is done, if all the forces are internal, then no external work is done, then we have the conservation of energy. We drop the work, and mv1 squared over 2 equals mv2 squared over 2. But we define other types of energy. This is the kinetic energy. We have energy due to a spring. We have potential energy. So there's other types of energy that we can add into this equation. But again, to understand the concept, no work, no external work, then the energy is conserved. And you can drop that term. Same thing. No impulse is added to the system, then we get, then we get the conservation of momentum. And that says the initial momentum is equal to the final momentum. Once again, very simplified. It says the linear momentum is the final linear momentum, but it works that we could include angular momentum if there's no impulse added to the system. All derived from our basic equations and substituted into F equals ma, and then rearranged into an intelligent, usable form that we can solve problems with. So that's the introduction to impulse and momentum and work and energy.